Alrighty, can you guys hear me?
Yeah, we can hear you.
Okay, how are we doing?
I'm doing well. How about you?
Hang in there.
That's good.
So we're getting towards the end of the course, and let me just give you an outline of what the plan is. So we're gonna have today. We're gonna have the splitting as we've done so many times before. We're gonna finish up radionuclidim theory. And then we're also going to finish up American derivatives. And the new big thing we're going to be talking about here today is this notion of a stopping time. And then the last topic, this is fixed income. And this is where we need, it's about Nicolan theory. So the last day of classes, if I'm able to read the schedule correctly, I asked Anna to confirm. Last day of classes is December 7th, right? So we will have our finals. All finals will be December 6th plus 7th. And so I'll send out an email with these time slots as last time, and you just reply with your preferred day. The last homework, this is number 10. This is going to be due on December 3rd. Yeah. Right, so there's no homework due for Thanksgiving. Right, and this fixed income topic, this is a big one. There are lots of problems on fixed income that are posted, and this is Reeve chapter 6. So that's the last. That's how the last part of this class is gonna be. We have a couple of lectures left to get all this done. Alrighty, are there any questions before we get started on? We've been talking about radionuclidim derivatives and American options for a few lectures now. We've done some homeworks on it. We've done lots of problems in class. Are there any questions before we get started? Right, so all exams are going to be the same as last time. There'll be some homework problems that we will be talking about. No, any questions or comments before we get started?
Actually, I guess I have a question. So like from the homework, I was talking about like when you're long a straddle and the straddle is strictly less than the sum of the price of the call and the put.
Yes.
How does that like doesn't make sense to me, because like in continuous time, a straddle is literally just a long call and long put. It's like it's the price of a long call and long put.
Yeah, this is a trick question, which is why it's there. So this is a question on the homework. It says why is put plus call prices? Why is the portfolio for put on a call? Why is the price of put plus call strictly bigger than straddle? Well, so let's try to let's try to discuss this a bit carefully. There were a few students that showed up with this question on the office hours last Friday, and so that it's a little bit complicated to get to, but let me try to start out with something that is easier. If I look at the European, then you agree, because then put plus call is equal to straddle. Right, and the reason that this is true is if I take a put, that's my put, it looks like that. This is my K, this is my K, I take the call, it looks like this. Right, and I take these two pictures and I merge them, I add them up. Right, this is equal to that thing, right? And I agree, for Europeans, this is true, but it's not true for Americans. So for Americans, then no arbitrage only gives you only gives us that put plus call is bigger than straddle. And indeed in the homework, this is possible. This is why what is going on? Well, why is it? I mean, why is this? What is what I'm writing here correct? Because my guess is that the top part here, this might be your intuition, but there's the word European in there, right? So when you get to the end of the number of time periods that your model has, whether it's continuous time or discrete time, you get to the end, the two payoffs they agree. But here it's different, and it's the fact that, so for Americans, you can exercise whenever you want. So for example, and this is probably what you want to do there, you wait till the end with the call. That would be my guess that you do this in the homework. And then sometimes you exercise the put early. This is when the price is sufficiently low, right? When the stock is sufficiently low. I'm hoping this is what you guys have been getting in that exercise, in that homework problem, that the call, you wait till the end. We're actually going to see this. We're going to see this today too. But for the put, sometimes when you're down at a low enough stock price, you would actually exercise. So for Americans, you can exercise whenever you want. In particular, you could choose to exercise the call and not, you could choose to exercise the put and not exercise the call. But for the straddle, you can only exercise one time. Right, so in particular, you could choose to exercise the put and the call at the same time. And if you do so, you're going to get the value of the straddle if you exercise the straddle at that time. That's why no arbitrage is going to give you the upper bound. But it's because when you have a put and a call, you can choose to exercise these two things at different times. And this is not possible with the straddle. The straddle is like a one shot. Over here, you have two shots. Right? So there's more flexibility on the left-hand side than there is on the right-hand side. And because of that, the left-hand side is going to be potentially more expensive than the right-hand side. So you have more flexibility. With the put and call compared to the straddle. Does that make sense?
Yeah, that makes sense. Like you're saying, like Yeah, they could just you could exercise early, so it has more of a premium.
I mean, you can also exercise the straddle early.
Mhm.
The thing that makes it strictly more expensive is that you can choose to exercise the put at some point, and then you can choose to exercise the call at some other point. So you have like two decisions to make here. You can make the decision on when to exercise the put independently of how and when you want to exercise the call. You don't have to exercise them in sync. But for the straddle, you only have one decision. Right, so you can, if you look at the picture here, you can choose to get the payoff here at a different time than you're getting the payoff here. And it's that additional flexibility that American options give you that allow for a portfolio of a put and a call to be strictly more expensive than just a straddle.
Okay, yeah, that makes a lot more sense now.
Okay. So it's always, I mean, they could be equal, right? But in this particular homework, you're not equal. Yeah. So for Europeans, I agree. They always get, because there's only one time where you can exercise, right? It's at the end. But for Americans, you can exercise whenever you want throughout the grid. Yeah. Are there other questions? Not, then we're going to continue with this Varaniculam derivative. We spent a lot of time on it, and the reason we spent a lot of time on it is because I know this has been tricky in the past, and because we're going to be using it. We're going to be using it in the next lectures, and of course, it's also going to be used in the spring semester courses. So Varaniculam. Or the Nicolam theory. So remember, so recall that dq dp, this is a random variable. So it goes from omega, and then it takes values over in. This is, remember that a random variable like this one is a Random-Nicolam derivative, Rn derivative. If, and then there are two properties. If what? If the expectation is 1, and 2, it was already encoded up here, but let me just write it out as a specific property. That if I compute the probability of dq dp being positive, it should be 1. So this one here was already encoded up here, but I just brought it out to highlight it. Then an absolutely continuous measure Q can be defined as how will we define it? We will define it as Q on a set A is defined to be the expectation of 1A, and then the Varaniculam derivative dq dp. Right, and this is true for any A in whatever sigma algebra that we're putting up here, typically F. Right, so it's a measure, it's a probability measure. It's a probability measure because if I took Q of omega, this would just be the expectation of dq dp. And that would be 1. Right, so it's a probability measure. It's absolutely continuous because if P doesn't see A, right? So if A is of zero measure under P, then Q on that set, Q of that set is also going to be zero. So these are just some notes we talked about last time. And then this, so the big result is that this property down here, this is, that's the definition of what it means to be absolutely continuous. So Q is absolutely continuous with respect to P. The Radon-Nikodym theorem says that if you have the structure here, then you can actually recreate Radon-Nikodym derivative. So this is if and only if. All absolutely continuous measures have that particular form. There are no other way to write them. And we looked at a number of examples last time, and one of the examples that I wrote down, I said, try to think about it, and then we'll talk about it next time. And so this time is now. Let me give an example that is more complicated than perhaps most of the other examples that we've been through. So the example starts out by saying I take two random variables, x and y. I'm going to make the assumption that they are standard normals. So the mean is 0 and 0, and the variance covariance matrix. So the variance of x is 1, the variance of y is 1, and then the independent, so outside the diagonal we have a 0. So these are standard normals that are independent. And then we take a constant, we take a theta, let's take theta in R. And then what I want to do is I want to create a new measure that's parameterized in terms of theta. Okay, so we're going to consider, so maybe this is the first part. So when is this expectation here finite? And we need a positive random variable. So I'm going to exponentiate it, and that's where the theta comes in. So I'm going to take theta here, and I'm going to take x and y here. And I want to know when is this finite. Okay, so how would one go about doing that? This is, a lot of you guys have done this in the homework in various forms and shapes. You have a constant, you have x, you have y, x and y are independent. You compute an expectation. This screams that we should use the independence lemma. Okay, so let's start out with something simpler. Let's start out by computing, say, the conditional expectation of x, given x. So now we can use the independence lemma, right? It says take out what's measurable. Take out what's measurable. Here, x is measurable. So we replace x by a dummy. Let's call it a, and then we leave y back as it is. And then my e is in the wrong spot. I have to move it a little bit to the left. Move it out here. Right, this is the independence lemma. It says then no more conditioning. You compute the unconditional expectation, and then you replace the dummy by what was measurable. So this was x. Right. So here, this is the independence lemma. So x and y is when the variables are independent. I condition on one. I just take it out and take the unconditional expectation of the rest. Okay. So how do I compute what I have in here? Well, it's theta A. Theta A, they are both constants at this point. Y is standard normal. And so Y is standard normal. That allows me to compute this moment generating function for the standard normal. And I'm hoping at this point we all feel comfortable about the moment generating function for the standard normal. For the standard normal. Do you all remember how that looks like? Yeah, what is it you do? You get an exponential. Exponential of what? Well, you'll take the coefficient in here and you will square it. You're going to get theta squared, a squared. And then the y, you're taking the average over it. You're going to have a half outside. And then when you're done computing, you put a equal to x. At this point, we're done computing, so we're going to write it as e1/2 theta squared x squared. Are we all good so far? So what we're really interested in is the expectation here. So we'll use iterated expectations. Iterated expectations. And they give us that the expectation we're hunting, this is e theta xy. This can be computed by taking the expectation of the conditional expectation. So this will be the expectation of the conditional expectation. Right, and that one we have, that was this guy in here. So we can write that out. This is an expectation. And now the inner part is what we had up here. This was e to the 1/2 theta squared x squared. But now what we need is the moment generating function, not for the normal, but for the normal squared. And more specifically, what we're really interested in is I want to know when this is finite. So one thing I could do is I could write this here out. Right, this here is using the standard normal density. So an expectation can, so here we're integrating over omega, so we can bring that expectation, that integral, we can bring it over into the codomain, so we're integrating over R. And the way you do it is by taking the function that you're computing the expectation of, so take this e to 1/2 theta squared, and then you replace x by a dummy. Okay, so let's keep calling the dummy for a. And then you multiply on to x's density. And x's density was 1 over square root 2 pi, e to the minus 1/2, a should still be a here, a squared, and dA, and then you're integrating over R. And what we're interested in, when is this finite? Well, to figure that out, what we need to do is we need to look at the exponent. So we have exponential here and exponential here. Here we have a 1/2 theta squared a squared, and here we have minus a 1/2. So for this to be finite, what do I need theta to satisfy? What do I need theta to satisfy? Well, if you face a problem of this sort, one idea is to plug in some values for theta. Like what would happen if theta was equal to 1? Well, if theta was equal to 1, so maybe just do some tests out here. If I take theta to be 1, theta is equal to 1, then I would have an integral over R of e to the 1/2 a squared, e to the 1/2 a squared, and I'll have a minus here of the same thing, and then I'll have this 1 over root 2 pi out here dA. Is this finite?
Yeah, that's finite.
What is the exponent? 1/2 a squared minus 1/2 a squared. This is going to give you e to the
0.
Yeah, and what is that equal to?
Isn't it 1?
It's 1. And so what do you get when you integrate 1 over R?
Oh, you'll get a, and then
Is it?
if you integrate 1 from minus infinity to plus infinity, you get,
Oh yeah, it'll be infinity minus negative. Oh, it'll be infinity plus positive infinity. So it's yeah, okay.
so that one doesn't work.
Yeah.
So let's try another one. What about if theta is equal to 0? Well, we still have this constant out there, which is not going to matter for what we're testing, right? That constant here is not going to change anything about being finite or not. So here, if I take a 0, what would I get? So then I would have the first term here would just be gone, right? And I have the other one. And what is that equal to? Well, what I have now here is I'm just integrating the density. The normal density is being integrated over R. So what's 1? It's just equal to 1. Okay, do we have any opinion over here what theta should satisfy?
Yeah, I guess theta should be 0.
Okay, so let's try another one. So another one. So what about theta equal to a half? Half, say. Then where were we going to get? We're going to get an integral over R. So see if I can do this properly. It's going to be e to 1/2 times theta squared. This is a quarter now. Times a squared. We also have minus a half over here. Times a squared. Is that integral finite? Well, what does the exponent come out to be? This comes out to be an 1/8 minus a half. Can I do this? This
No,
is,
it's still infinite.
you're saying this is equal to plus infinity?
Yes.
So an 1/8 minus a half, is that positive or negative? This should be something like negative 3/8. So if I integrate e to the minus 3/8 of a squared dA, is that not finite? I think this is finite. So there's more than just theta equal to 0. There's also like theta equal to a half. What else is in there, right? The thing to look out for is if you want this integral to be finite, you need the exponent to be negative. So if you want the exponent to be negative, you cannot have that theta squared is too big. You're going to need something like theta squared is less than 1. Right, so theta belongs to minus 1 to 1. So this was step 1. When is this thing here finite? Well, that happens if and only if theta squared is less than 1, strictly less than 1. And that was important because now we can, so for step 2, we want to know, and now we can sort of let theta be in this interval here. Then we can define Radon-Nikodym derivative by exponentiating theta with x and y. But keep in mind, we always need these things to have expectation 1. Keep in mind, we always need to have them to have expectation 1. So we need to normalize to get a random variable that has expectation 1. And the way we do that is simply just by dividing by its expectation, e to the theta xy. And this is where we need a step 1. So we need a step 1 to make sure we don't divide by plus infinity, because if I divide by plus infinity, I'm just going to get a 0 here, and I don't want that. So this is where we need to figure out what theta this would work for. And this here is then strictly positive. So we call this property that, so this measure Q is equivalent to P because the Radon-Nicolam derivative is strictly positive. So P is absolutely continuous with respect to Q in this case. The formula here will always give you Q being absolutely continuous with respect to P, but because it's strictly positive, it also goes the other way. If Q is equal to, if Q of a set is equal to 0, you also get that P is 0 on that set. This was something we talked about last time too, right? This here means that Q is absolutely continuous with respect to P, and P is absolutely continuous with respect to Q. So now I have my new probability measure, and the question we want to ask is, what is the distribution of this vector here? Like under the measure P, like this here is under P. Under P, X and Y were standard normal. They were independent. They had zero means. They had variances. Each one of them had a variance of 1. So now I'm creating this new measure, and I want to know what is the distribution of this vector, not under P because that I already know, but I want to know what it is on the Q. How do we figure that out? Any guesses on how we should go about solving this problem?
Isn't there a relationship between the P measure and the Q measure involving the Radon-Nicolam derivative?
Yeah, and what? So in general, if you were to figure out what the distribution of a random variable is, how would you go about doing that, Eddie? What kind of a tool would you resort to?
Not sure.
How can one go about characterizing distributions? We can compute a number of different things, but in particular, we could compute.
Would it be moments of the?
Can you say that again?
Would it be moments of like the random variables?
So moments we could do, but see here, this thing here is not finite for all thetas. So by doing moments, we could run into a mess because they might explode. So instead of the moment invariant function, we could compute what function?
The characteristic function?
Yes. So let's compute the characteristic function on the Q, right? Because that's where we're working. So the characteristic function goes by e to the, and then there's an I here, and then say there are two of them, so it's like t1 times x plus say t2 times y, and we're going to compute it here on the Q. What is that equal to? So we need to remember, and we talked about that last time too, there's this lemma that says that if I want to compute an expectation, and this was what Eddie, I think what Eddie was referring to, was that we need to bring this expectation on the Q, we need to bring it back to something on the P, because it's on the P, I know I have independence of X and Y. And the way to do that is computing these expectations on the Q. Well, that's equivalent to multiplying onto the Radon-Nicolam derivative. So here we'll have dq dp. It goes inside here, and then you have your function. The characteristic function comes in after. right? And then you compute an expectation here, but now this is on the P, over here is on the Q. And now over here, I'm good because I know X and Y are independent. So can I compute something like this? Well, let me plug in what the formula was. The formula was this one, right? I take this expression here and I substitute it in on the next slide. Knowing full well that this here is a constant, I can pull him outside the expectation if I so want to. So I can write this here out as 1 over, and then the expectation of E theta xy, and then the remaining expectation, this was E theta xy times E, and then it's I T1 x T2 y. And what do I mean, how do I go about computing this then? Well, one thing we can do is we can, I mean, there are a number of ways forward here. One thing we could do is we could proceed as we did before by conditioning on one of the two, and then that would give me yeah, maybe we should do that. So again, use we can use the independence lemma. Use the independence lemma, we will get that we have theta xy here, then you have EI T1 x plus T2 y. If I would condition on one of them, say I condition on x, so that means that everywhere on the inside, I will replace x by a dummy. So let me call that dummy for A as we did before. So I get that one. Plus I T1, and then x was replaced by A, plus I T2 and my y. And then we could condition, we have to replace, when we're done with the conditioning, we have to replace the dummy by the random variable x. And now this looks slightly better because, well, this is a constant coefficient. I don't have to worry about him, and then I just have y's in here. So I can write all this out as, what will I have to write out here? I'll take E I T1 of A. And then what I'll have left inside will be E, and then I want to put an I outside. We've got T2. And then here, what do I have? I have A times theta, and I have an I outside, so I should put a minus an I there. Theta A. Just a sanity check. I get I squared is -1, so it adds over what I have here, and then I put a y all the way outside. And then I need to put x equal to A when I'm done computing. So this would be one way to attack it, and now you can compute what you have here, because you know that y is standard normal. This is one way to work out what this expectation here is. Let me just show you perhaps a simpler way of doing it. If we just resort to Mathematica and let Mathematica do the hard work for us. Let me go down to somewhere clean. I'm hoping everybody can see Mathematica. So if I know my density, my standard normal was equal to exponential of -1/2 times A squared divided by square root of 2 times pi. That was the standard normal density, and now I have a two-dimensional object, and I'm computing. I'm interested in integrate exponential of my parameter theta times x times y. That was my Radon-Nicotinum derivative, and I need to multiply onto the density. So here I'm using that x and y, they have the independent on the p, so I can evaluate f. So the joint density is going to be equal to the product. This here was that expectation we calculated, we proved was finite in the very beginning, and so maybe just see what Mathematica says if I ask Mathematica to compute the expectation. So here we should get finiteness, provided that theta squared is less than 1, and otherwise it should blow up to plus infinity. So if we run it, just clear out the kernel. So if we run it, if you run it, it won't do it. Oh gosh. Maybe it's because I should get this thing there and then try again. And then we just have to wait and see. So there you go. So this was that expectation, and you can see the condition that Mathematica is coming up with. It says that the real part of theta squared has to be less than 1. This was exactly our expression as well. So here we have this expression for that we just copy pasted into my sheet. That bottom expectation here, we figured out that this was equal to 1 divided by √1 minus theta squared. Now, we also want to know what this thing here is. Can we compute what that is in Mathematica? So we're saving ourselves a little bit of trouble. Well, let's try it. The thing that changes is I need to have another term here. I need to have exponential, and then it's I times T1 times X plus I times T2 times Y. So can Mathematica also help us here? And let's try to run it and see what it says. And it comes out with a long and messy expression here. Again, it says that this thing is finite provided that theta squared is less than 1. It's like it won't recognize the I. Maybe the syntax is wrong. Put in a capital I here. And so that looks better. This is that's the characteristic function computed under the measure Q of our random variable, and you can see the coefficient. You can see the coefficient is this. You divide by. You can pull the square root of half outside, and you're going to get 1 minus theta squared here. Now, what's interesting is what's upstairs in the. How do I make this thing bigger? We can see it. How do I make this thing bigger? Size. Where's the size?
The upper right, can you zoom it in?
Which one do I hit?
I think it's 100% in the upper right of the screen. I'm not sure.
That's the one. There we go. Now we can all see it. Okay, so we have the coefficient outside. We have the coefficient outside, and then we have this exponential in here. And that's the thing that's interesting. Because how does this coefficient here compare to the independent case? Well, had X and Y been independent, what you would find here would simply just be the characteristic function, two independent normals. So had, maybe I should write this down. So had, so under P, we will get that the expectation of EI T1X plus I T2Y, this would be equal to, we'll take the product because they are independent. And then we would get e to the minus 1/2 T1 squared times e to the minus 1/2 T2 squared. That would be under P, and this is because here we're using that they are independent. So under Q it's different. Under Q it's different, and let me just copy paste what I had in the in the formula. This would be the expectation EI T1X plus I T2Y. This became something more complicated. And what you ended up having was e to the, so say it's minus 1/2. Yeah, so say it's minus 1/2, and then downstairs, minus 1/2, and then you have 1 minus theta squared down here. And then inside you would find T1 squared, and then T2 squared. And then you'll also find 2 T1, T2 theta. So you see, it's if theta here would be equal to 0, if theta would be equal to 0, these two would agree. If theta is equal to 0, then these two would agree. So what comes to mind? What could theta probably be here? So when theta is equal to 0, they agree. That's perhaps not a surprise, because what happens when theta is equal to 0? Well, when theta is equal to 0, the Radon-Nicolam derivative becomes 1/1. So the Radon-Nicolam derivative becomes 1, which means that Q is equal to P. So at least this makes sense. But in general, what does it look like theta is? Well, theta here seems to control the mixture. This theta here seems to control X and Y, how they relate to each other. And so I wonder if it has anything to do with correlation. And how would we figure out what this here is? I mean, the ultimate goal was to answer the question, what is the distribution? What is the distribution? What is the distribution of X over Y under the measure Q? Any guesses on what kind of a distribution corresponds to such a characteristic function?
Is it chi-squared?
Is it chi-squared? I don't think so. So how would I go about doing it? Let me just make sure I have this site open. Can you guys see my browser here?
Yes.
Okay, so go to Wikipedia and look up the multivariate normal. So here you have X, this is my vector, X is, and the distribution has a mean, and then it has a variance covariance matrix. So if you go down here, it says the characteristic function of X has this form. The characteristic function of X has this form. So there's a mu here, and then there's a variance covariance matrix. So if you try to work out, so mu, let's just forget about mu and just focus on, let's focus on the second part that involves sigma. So I'm looking at the exponential of -1/2, say t. So what does it say? ut, so that's t1, t2. Then there's the variance covariance matrix sigma, and then there's t2. This here is the standard. This is the standard. This is the characteristic function for a multidimensional normal. This is the variance covariance matrix. So let's work out what this is and see if it falls into this category up here. Well, this is going to be the exponential. This is going to be the exponential of -1/2, and then t1, t2. Variance covariance matrix, how does that look like? Well, you're going to have a sigma 1 up here and a sigma squared down here, and then off the diagonal, we're going to have the covariances. Right, so the covariances between x and y, and the covariance over here between x and y. And then we're going to multiply onto the vector t1, t2. Right, so I'm trying to make this expression up here look like that one down here. And let's work out what it is. Let's work out what it is. So we need to be able to multiply a matrix with a vector. I think we can do that. So it's t1, t2. Then you multiply sigma 1 squared with t1. And then the covariance gets added on between x and y to t2. And then the bottom one is the covariance between x and y with t1. And then added up sigma squared, sigma 2 squared times t2. And so what does all that stuff become in the end? It becomes the exponential of -1/2. And then t1 gets multiplied onto the top part. This is sigma 1 squared, it's t1 squared. And then you're going to get two of these. You're going to get two of these. So this is 2 t1, t2, and then the covariance of x and y. And then finally, you're going to get t2 sigma 2 squared, t2. So can you match up now what we have up here? But it surely seems like sigma 1 and sigma 2, they're going to be the same. And what you're going to be is this 1 over theta squared. So match up the two expressions. So sigma 1 squared. Sigma 1 squared is what is going to get multiplied into t1 and t2 squared. Okay, so that's going to be 1 over 1 minus theta squared. This is the same one for the second guy. And then finally, what's the correlation? So we have 2 times t1, t2, and then this covariance. The covariance is going to be, there's a theta here, and then there's 1 minus theta squared here. So the covariance of x and y is going to be theta divided by 1 minus theta squared. And of course, we can express the covariance in terms of correlation, right? The correlation between x and y is the covariance x and y divided by the standard deviation, sigma 1, sigma 2. And if you plug all that stuff in, the covariance was theta over 1 minus theta squared. We have to take square roots here. So this is going to be the square root of 1 over 1 minus theta squared times the square root of 1 over 1 minus theta squared. This becomes, the square roots cancel. We just left with theta. So you see under Q, x and y, you're going to remain normal. The mean is going to be 0. The variance is going to change. The variance covariance matrix is going to change. This is going to be 1 divided by 1 minus theta squared. That's going to be the variance of x. And the same thing over here. And then the covariances of the diagonal are going to be theta divided by 1 minus theta squared and theta divided by 1 minus theta squared. This here is the distribution on the cube. So by multiplying onto this Radon-Nikodym derivative, we alter the covariance and we alter the variances. The question about could it be chi-squared? It made me think, like, why could it not be chi-squared? So why could it never be chi-squared? Remember the exercises we had last time? We were playing with normals and exponentials. So here we know that P and Q, they have the same null sets. Right? If P is equal to 0, then Q is equal to 0 on that set. Q is equal to 0, then P is equal to 0. Right, so if say X was chi-squared under Q, well then, if I look at the probability that Q of X would be negative, what would that probability be if X was chi-squared?
Be 0.
But what about P? P of X being less than 0 is equal to 1.
A half.
Right? So this D cannot coexist because we know they share the same null sets. This is because dq dp was strictly positive. Right? So it cannot be chi-squared under one and then be normal under the other. These two measures are not going to be equivalent. And that is guaranteed because the Radon-Nikodym derivative is strictly positive. So we cannot have that. Are there any other questions or comments about this example here?
Professor, earlier on in this example, used the iterated expectations.
Yes.
And could you just go over that really quick again?
Yeah. So iterated expectations. If I have so say I have two sigma algebras H inside G. Well, then if I compute the expectation of a random variable, let me not call it X and Y, let me call it something just arbitrary, like A given G. Or maybe, so here if I take H, iterated expectation says that I can put something bigger inside here. I can condition on something bigger and then condition on something smaller. This is iterated expectation. So what we use this property here for was just to say H is equal to the smallest sigma algebra we have. In that case, the left-hand side becomes A and the right-hand side becomes the expectation of the conditional expectation And this goes to this idea that conditional expectations are to be thought of as estimators. Right? So given H, given the information that's in H, then this is my best estimate of A. Right? And estimates, they of course are in here the random variable, right? So this is an estimate of A, depends on whatever I can observe, whatever the sigma algebra H is. But it has this property that if I take the expectation of it, if I take the expectation of my estimate, I'm going to get the correct expectation. It's not going to be true if you moved into variances. It's not going to have the property that the estimate has the correct variance or higher moments, but it has like the correct first moment. Yeah, other questions? So this is this was an elaborate example on a random different derivative. So a random different derivative is just one random variable. So sometimes, and this is what we're going to be doing now, we're going to be looking at the random different process. So let me just write out what that is. So dq to p, this is one random variable. And it's called the random different derivative. Now, we often have a filtration. We often have a filtration, maybe up to n. We often have a filtration, and then we can speak of the Radon-Nikodym derivative process, and it's defined by take the expectation of your Radon-Nikodym derivative, and then you condition on Fn. So now this is a stochastic process. It goes from 0, say, up to n. So when you just have a dq to p, this is one random Nikodym, this is one random variable, and we call it the random Nikodym derivative. When you have filtration, we can form this conditioning here, and of course, this goes back to properties that we have looked at a bunch of times. This object here, this is a martingale. This is a martingale, and this is going to be on the p. Let's just do the proof again. This object here, this is often called Cn. And so what we need to do is we need to take Zn plus 1 and then condition on Fn. We want to compute what this here is, and we want to show that it's equal to Zn. So again, as was just asked about, iterated expectations is what's going to happen here. Because what is Cn plus 1? Well, Cn plus 1 is this object here when n is equal to n plus 1. So we plug that in. So that's my Zn plus 1. And then I have the condition on Fn. And now, Eddie, which of the two sigma algebras win?
Would be the smaller one, F.
Yes, very good. So the smaller one wins. Right, and that was my Cn. Right, so this, the Radon-Nikodym derivative process is a martingale. There's no doubt about it. And we had, I think that was maybe 2 times ago, we had looked at 4 different specifications of this Cn process. So now we're going to return to them, and in particular, the one I want to return to is the one that we're using in the binomial model. So the example is, our main example is Zn being, you take, what did you take? You take P divided by P tilde divided by P raised to the power of number of heads in the first n tosses times 1 minus P tilde divided by 1 minus P to the number of tails in the first n tosses. Do we remember that one? This is from a few lectures ago. We proved that this was a martingale, like this Hn here. This is a number of heads in first n tosses. And this one here, this is the number of tails in first n tosses. That's the Radon-Nicotinum derivative in the binomial model. Do we all remember this one? So one property that we've used is when we're on the P we have these guys are, if we run up to n here, these are IID Bernoullis. Right, so you go to up and you go to down, probability P, probability 1 minus P. And the IIDs are the independent and they all have the same distribution. But what we've been using that that the IID Bernoullis under P tilde. Right. So here you have P tilde, go to U, 1 minus P tilde, go to D. But as we saw, we just saw an example where X and Y, they were independent on the P, but not under Q, and P and Q you were equivalent. So we kind of have some work to do here, right? We're given that we have IID Bernoullis on the P, but we've actually been using the property a lot on the P tilde. And as we've seen, just because you have an equivalent measure, it does not show that you have independence. That does not carry over on the equivalent measures. And we just seen an example where theta comes into play and it controls the covariance. So we owe a proof here. There's no way around it. We owe a proof of this property. Like, why is that true? So let's show. So let us show that. Let us show that S1 over S0, which is my psi 1, that this indeed is independent of, well, S2 over S1, which is my psi 2, on the Q, on the P tilde. How do we prove something is independent on the P tilde? Any ideas? How do we prove something is independent? Yeah, how have we done it before? If you have two random variables, we want to understand their joint distribution, such as, for example, independence as here. How could we do it? Any suggestions?
Isn't it that we show that the characteristic function of the joint of psi1 and psi2 is equal to like them separate, multiplied separately?
Very nice, very nice. This is exactly what we need. So that's the joint one is when you have a T1 and then you have IT2. Like, let's show that this thing here is, we want to show this. So I should say something like, it suffices to show that the joint characteristic function is given as the product. EIT2. Right, and the only place that this stuff can come from, it's going to come from the fact that this property is true under the P measure. So if I deleted the tildes, this is true, but now the tildes are there and we still have to prove it. Okay, so let's go about doing this. How would we go about doing it? Well, as before, you multiply it onto the appropriate Radon-Nikodym derivative. So here you need something that goes up to time 2. So now we have a Radon-Nikodym process. So we could, on one hand, we could put in dq/dp. Okay, so that's, I'm going to fill in a bunch of steps here, and then in the future we won't take that many steps. But computing expectation, you multiply into dq/dp. Then you have EIT1 psi1 plus IT2 psi2. And then what we could do is we could use iterated expectations one more time. We can say that the expectation is equal to the conditional expectation. T2 psi2, and then we condition on, say, if2. Right, and now this will be measurable, so you can travel outside the expectation. So this is measurable, you can jump outside. And then what I'm left with is dq/dp's conditional expectation on f2. Well, that's my Radon-Nikodym derivative process at time 2. This one here, this is my Z2. I mean, we know what C2 is. We know what C2 is because that was how we had it in the beginning. Like, we know what C2 is. C2 is this quantity over here. When n is equal to 2, we get the number of heads in the first 2 tosses, number of tails in the first 2 tosses, and so on. And let's plug that in. Get EIT1 psi1 plus IT2 psi2, and then comes the Radon-Nikodym derivative. This was P tilde over P to the number of heads in the first 2 tosses times 1 minus P tilde divided by 1 minus P to the number of tails in the first 2 tosses. Right, and I want to prove that this stuff here is equal to what I have over here. But of course, I can also work out what the right-hand side is. I can go through the same sorts of calculations as what we have here done on the left-hand side. Right, I want to see if I can match it up. So how would one do it? Well, I want to use the independence property that I have. It was given to me from the very beginning that these coin flips, they were IIDs on the P. And that's the property that I want to use. That's the property that I want to use to compute this expectation here. But I have the number of heads and number of tails in the first 2 tosses. So I need to make that a little bit nicer. So let me group them. Let me group them as EIT1 psi1. And then what I have here, I will have the P tilde over P, and then the number of heads in the first toss. And the same thing for the other one. This is 1 minus P tilde over 1 minus P to the number of tails in the first toss, right? And this here is my Radhanickel derivative at time 1. This one here is my Z1. And then I have the left part. This will be E2, and then this term here is left, I T2 psi 2. And then of course I borrowed something here, so I need to correct for it in the second part. This is P tilde over P, and then there's the number of heads in the first 2 tosses minus the number of heads in the first toss, right? To get these things to cancel out. And then we have 1 minus P tilde divided by 1 minus P, and we do the same thing for the tails. Number of tails in the first 2 minus the number of tails in the first. And now I'm in good shape because this here just involves the first one, and this one here only involves the second one. So they are independent, and I can use the independence lemma. They are independent, and I can break the expectation into the product of the 2 individual expectations. So I'll do that. This will be EI T1 psi 1 times Z1. And then the other one will be EI T2 psi 2. And then I'll have P tilde over P times the number of heads minus the number of heads in the second toss is what I have here, times 1 minus P tilde, 1 minus P, and then the number of tails in the second toss. So I'm almost there. The only thing that remains is I'm hoping to get it to look like this. And the first part is now good because I have my Z1 here. I absorb it into a change of measure. This will be exactly E tilde of EI T1 psi 1. The second part is slightly more problematic, but it's not that bad because what I can do is I can multiply and divide. I can multiply and divide by the expectation of C1. Like this one here, this is equal to 1, right? Because it's a martingale. So the expectation is constant over time. And then I can have the same quantity as before. P tilde over P, number of heads. I'm just copy pasting what I had up top. Right, and this here only involves the first toss. This here only involves the second toss, the independent. I can bring them together, and I can write this here as EIT1 psi 1, and then this expectation and that expectation because of independence between C1 and psi 2. So this one here uses that C1 is independent of psi 2. I can bring them together, and what I'll be left with is EIT2 psi 2, and then inside here I'm going to have exactly these terms, the T1 and the H1 term, and you'll cancel out, and I'll just be left with C2. And that's great because now I can absorb it into the change of measure. This will be my EIT2 psi 2. And that was exactly what I was hoping for. Right? This was what we want to show. We wanted to show that. So we went through all these calculations finally to get down to saying, well, it is really true. That complicated expression has this nice product structure. Any questions on what we've seen here? It looks messy, right? But that's because the Radhanickel derivative in the binomial model, it's unfortunately pretty messy, right? That's the formula that we have to work with. Are there any questions on what went into the various quality signs on these sheets of paper? So it was again, the starting point was this conditional expectation. So when you have a random variable that only involves the first 2 coin tosses, then you use the random nickel derivative process evaluated at that time. Had there been like 3 in here or 4, then you would need to have z, however many you have. If it's up to 3, then you need to have z3 instead of just c2. Are there any questions on this? So this thing here has been this is a problem that's been dangling out there for a while. All right, let's just spend a few more minutes and then we'll take a break. The last thing I want to say about this random nickel process is that there's also there's a martingale hidden. There's a way to use. There's a way to use. So we have. So we know that Zn, and we also know that we know that Zn is a P martingale, and we know that, for example, that the discounted stock price, this is a P tilde martingale. So one could ask, what is the relationship? What is the relationship? What is the relation between P and P tilde martingales? And this is coming from Bayes' rule. So Bayes' rule, we call that a lemma. Bayes' rule says that we always need to have interoperability. So we're going to have that say dp tilde dp times a y, say that this is finite, take absolute value to be sure. So again, this is just a technical condition. It's always going to be satisfied in the models that we have. Let this thing be true, then if y is, say, fm measurable, and I take a number m bigger than n, then so we take a random variable which is fm measurable, then what we have is, if I'm looking at the conditional expectation under that tilde measure of the random variable y given f and a condition on the smallest number, the way you go about computing this is you multiply in, so this is on the tilde measure, so you multiply in the random nickel derivative. Y here lives up to m, so you multiply into cm here, and then your y, and then you condition on fn, and then you divide by cn. This is how Bayes' rule looks like for conditional expectation. So it takes you from probabilities on the one measure, and you can restate them in terms of probabilities on the p, but you have to be careful about the random nickel derivative. So just a sanity check. When n is equal to 0, what does it give us? Well, then we're conditioning on the trivial sigma algebra. We're just going to get the expectation of y. Well, this is then going to be equal to the expectation of cm y. And then we're dividing here by z0, but that was 1. So this formula here was exactly what we used on the previous slides. You say that you have an expectation. I know that y is measurable up to some time. And then what you do is you multiply in that random negative derivative up to that time. So it's consistent with what we have done. And maybe I should give an application. So instead of taking you guys through the proof, maybe we should look at an application. Say, what should we say? We should say that Mn is a martingale on the P tilde. Well, then Zn times Sn, there's no S, it's M. And Zn times Mn is a martingale on the P. And so let's try to prove that. Let's try to prove that. So say that Mn is a martingale on the P tilde, then you multiply onto the Radon-Nicotinamide derivative and you're going to get a martingale on the P. So let's try to work that out. So we will do, the assumption is that if I take Mn plus 1 condition on Fn, I'm going to get Mn, right? That's on the tilde, that's on the, that's the assumption. And now I want to prove that. But I can use Bayes' rule. This is Bayes. I can use Bayes' rule. He says, if I'm interested in computing this conditional expectation, what I need to do is I need to write it as an expectation on the P. Where is the measurability here? This is M, so this is n plus 1 here. So I need Zn plus 1 times my y. My y is Mn plus 1, given Fn. And then I need to divide by Cn. And there you go, right? Now I just move the Zn to the other side, and I get Cn plus 1, Mn plus 1, given Fn. This is equal to Zn. So for example, if I take Mn to be the discounted stock price, right? So the discounted stock price was Sn divided by 1 plus R to the nth. This is a P tilde martingale. Okay, but then I know that Cn times Sn divided by 1 plus R to the nth, this is a P martingale. So it gives us a way to move, if you're interested in the martingale property on the one measure, I can restate that martingale property in terms of a different measure and the Radon-Nicotinamide derivative process that takes me from one measure to the other. So we have had a lot of Radon-Nicotinamide derivative the last few weeks, and this is at the end of what I wanted to talk about. Are there any questions on this before we take a little break?
Hi, Professor. In the expression you had above, when you have for Bayes' rule, is what can we do for, so like, is M any arbitrary number when we have Bayes' rule, or is it just like, yeah?
This one.
So where do we? Yeah. Okay.
It ends up to where this one lives. So if you're on a finite time horizon, then M here would have to be less than capital N.
Okay.
So, and then I don't think we're gonna have any. Normally after this chapter, we would move into chapter 5, and chapter 5 is all about, so let me just write that here. Chapter 5 is all about infinite horizons. But because we've changed things around, we spent more time on Hull. If you're interested in this, then if you would have an infinite time horizon model, then you would have to put, then M can be arbitrarily big. But if this dp tilde dp, if that lives on F capital N, then there's no way you can go any further than F capital N.
Okay. Thank you.
And this base rule here, this has nothing to do with discrete time. This base rule here works just as well in continuous time. Yeah, so it goes up to capital N, and then it can be anything in between. Yeah, other questions? Okay, so after the break, we will talk about stopping times and American derivatives. So let's take a little break and get back together on the other Sulik.